Okay, so I'm recording. I think I'm recording this. Let me just make sure. Okay, good. I'm recording. So hi, everybody. I'm here in beautiful San Francisco in the Hilton. It is now only 7:48 a.m. Well, it's 10:48 a.m. there or 10:49, whatever. Yeah, so I'm just waiting for the poster area to open so I can hang up my poster and then go for a walk to get ready for business today. All right, so today what we're going to do is we're going to cover odds ratios. I know I covered it the other day a little bit, but it was very quick and I want to make sure we get everything correctly. So let's go over everything. I'm going to show you how to do the calculations and get you ready for, the exam to come. On Tuesday, I'll do a exam preview for you since our exam's not till Thursday next week. Thursday next week. All right, so odds ratios, remember odds are the probability of success divided by the probability of failure. Okay, so odds are the probability of success divided by the probability of failure. An odds ratio is just a ratio of two odds, where here we can use odds ratios to do anything. We can predict the odds that somebody will come down with a disease, just like we did with relative risk. Relative risk, we looked at the risk somebody has if they're exposed versus the risks they have if they're not exposed. But here we're looking at the odds of somebody getting a disease if they're exposed versus if they're not exposed. However, the benefit of odds ratio versus relative risk is we can also look backwards. So we can do something like a case control study where we're looking at cases, people who have the disease versus matched controls, people who don't have the disease, but they're matched on some variable to make them as similar as possible. I mean, you can't randomly assign people to disease versus not disease because they already have it. And we look backwards at their exposure. So that's what we're doing here. And because of that, we can use the odds ratio, but we cannot use relative risk because risk means new cases. And if you already have the disease, you are not a new case. And here I showed you what it means, success and failure. So success is whatever you're looking for. So probability of success would be whatever you're interested in. Like it could be the probability of having cancer, which clearly is not a good thing, but in statistical language, it's a success. So that's the probability of success. And then the probability of failure would be the opposite, the complement of that. And so I'm sitting in this shared room here. Hi. Sorry, you don't mind if I'm doing a video? No, thank you. So I'm sitting in this shared room here. So we mark probability of failure just for simplicity's sake with Q. So it's 1 minus probability of success. So those two are complementary events, and success and failure are the only two elements of that specific sample space. So they have to add up to 1. Probabilities always have to add up to 1 of all possible events within a sample space. So that's why I do that, since I show you that there, just in case you didn't have stats before. So like here's an example. What's the probability of rolling a 6 with a fair 6-sided die? I'm not talking about a gaming die. So if it's 1, 6, the probability of not rolling a 6 would be 1 minus 1, 6, or 6, 6 minus 1, 6, or 5, 6. Okay. The odds then would be the probability of rolling that 1, 6 divided by 6, 6, right? 1, 6 divided by 5, 6, right? So we can like calculate odds always by getting the probability of success divided by the probability of failure. I talked to you about a case control study already. So here's a really nice example, and I showed you this the other day. So we're looking at the odds of exposure among those who have the disease versus the odds of exposure among those who don't have the disease. And I showed you that when we calculate the odds ratio, so it'll be A divided by C, because success would be exposure, failure would be not being exposed, right? Among those who have the disease versus those who do not have the disease. When we bring that denominator into the same level as our numerator, we get this, we have to invert the denominator and we get this really nice pattern, this cross pattern that you get with odds ratios, right? A times D, and here C times B. Now, the only thing you have to do when you're doing this is just make sure you're aware of what you're looking for so you don't report the wrong result. sometimes people report wrong results with odds ratios because they're not paying attention very well. The confidence interval for the odds ratio is a little bit wonky, if you want to say that. But if you're interested in learning about it, you can watch my video. I do the proof of this. So this is what's known as a delta method standard error. And I'd mentioned before, when we were calculating confidence intervals, everything's done in the exponent of this of e here, right? So we're exponentiating. We're exponentiating because the confidence interval is heavily skewed to the right, because one is like the equivalent of a zero when you talk about odds ratios, because a one would only be attained if you have equal odds for exposure versus non-exposure. So that's a non, there's no difference, right? So you get a one, but then the odds ratio can only go to zero. So you've got this distance between one and zero, and then above one, you can go on and on and on, right? So it's highly skewed to the right. And because of that, we have to use what's known as the delta method standard error because our variance is skewed. And then also, oh, well, excuse me, the odds ratio is skewed, right? So we have to do that. And then the variance is also skewed. So we have an issue there, and we have to, in order to calculate it, we have to use this thing called the delta method standard error, which, when I started looking at this for the first time, it was like really, whoa, where did they get that? So I took time to prove it. And again, if you're interested, you can see the proof. But this is one over each cell, like one over A plus one over B plus one over C plus one over D. So odds ratios can only be done in a 2 by 2 situation. Now you can have 3 by 2, 4 by 4, whatever, but you can only do it in a you have to shrink things into a 2 by 2 to use an odds ratio. Here's the equation for calculating the confidence interval. So this is similar to what we did with relative risk. Everything's up here in the exponent, right? So we're doing this, like we're taking the natural log of the odds ratio to hasten its conversion to normality. And here we're also, again, we're using the standard error, delta method standard error. This part to the right of the plus minus sign is the margin of error. And because we're using a standard normal distribution, so that's what we're doing. We're using 1.96 to demarcate the middle 95% of the distribution, positive or negative 1.96. And this is only applicable to a 95% confidence interval. And as I mentioned, because this isn't a stats class, we're just going to use 1.96 here. If it was stats, we'd vary this for different types of confidence intervals. Okay. So in order to solve this, what we have to do is we have to compute this in the exponent level here, and then at the end we exponentiate it to bring it back into an odds ratio scale. Okay, so let's do a couple of those using Excel. So here we have table 3. Using table 3. Where's table 3? Table 3. Where's table 3? Using table 3. Here it is. Okay, so we're going to calculate the odds of exposure, right? The odds of exposure among cases versus controls. We're doing an odds ratio. So we have 50. Well, let's go straight to Excel. Okay, let's go to Excel. Here we have odds ratio. Oh, here it is. This is the one I'm looking at. Okay, I might have these backwards, but you can figure that out, right? Okay, so this is question 3. Oh, okay, here it is. Okay, pretend that table 2 repeated below represents a case control study instead of a cohort study. Calculate the odds ratio for texting while driving given one had an accident versus not having an accident. So our condition in this case is accident versus non-accident. And then we're looking to see what's the odds of exposure, and that's texting by driving. So this is a prototypical case control study. Okay. All right. So we can calculate the odds of texting while driving just by dividing success, which is 36, divided by 28. And then for the controls, it's 364 divided by 572. So let's go to the video. Here it is. All right, so if you look at how I set this up, and again, you can plug your numbers directly into the table. As long as you have 4 cells, I don't care what you're comparing, just plug them in here. So the odds are C4 divided by C5. So C4 is 36 divided by 28. And the same here, we have D4 divided by D5, right? All right, so we see that we have greater odds among the cases than among the controls, which is what we expect to see. And our odds ratio is dividing C7 by D7 again. So I set it up so this is like a beautiful little tool. You can just plug anything in, you get your odds ratio. So you get an odds of 2.02. So that would translate into a basically a twofold increase in the odds of texting among cases versus controls. Twofold, or it's 100 times increase because you're going from 1 to 2, that's 100. But we don't talk about 100% increase. We talk about, excuse me, not times 100% increase. We talk about a twofold, threefold as we go further and further up the chain. All right, so that gives you your odds. So now we need the confidence interval. So what I did here, I divided this into A, B, C, D, right? So A, B, C, D. And for each of those, I divided it into N. I took its reciprocal, right? Divided it into 1, N into 1. And then I summated them because that's what we need, right? We need to sum them, right? And then to get the standard error, we take the square root of that sum. So you can see that I did this in a very methodical way so you can to ensure that you get everything correct. When you're doing your exam, I just want to see you write out everything. You can use this tool. That's awesome. It'll get you the right answer, guaranteed the right answer, but you just got to show me the work, okay? Margin of error is 1.96 times the value here. Now, I also need the natural log of the odds ratio because if you recall, the equation was here, natural log of the odds ratio times the margin of error. So we take the natural log of the odds ratio, and we get 0.7033. As I mentioned before, if it's above 1, you're going to get a positive value here. If the odds ratio is above 1, you get 0.7033. Next step is to complete everything in the exponent. So we get 0.7033 minus the margin of error, 0.511, and you get 0.192241, and then we add the margin of error also to the natural log of the odds ratio. So these are our two values. Finally, we exponentiate them. So if you look here, I use this function exp, right? That's available under math and trig. And I got my confidence intervals 1.2. Well, I'm gonna make this smaller, 1.22 and 3.368, because I always go to 1.222, 1.212. I always go to three significant digits. So how would I, sorry, my knee's hurting. How would I interpret this? So we'd say that cases are slightly over 2 times more likely to have texted while driving versus control, or people who had accidents were slightly above 2 times more likely to have texted while driving versus controls, or versus those who didn't have an accident. So this is my point estimate. It's 2.02. So it's my estimate of the population value. Again, this is an inference we're making. My true value, though, is between 1.212 and 3.368. Okay, so let's go to the next item, or the last item. Item 4, using table 3, calculate the odds ratio of exposure given one has the disease D versus not having disease D. All right, so where's table 3? There it is. Table 3, I like disease D, named after me, right? So, all right, so here we have, what do we want to do? We want to know the exposure. Okay, so our success is being exposed. So 50 exposed, 25 not exposed. So it's 50 divided by 25 among cases, and 100 divided by 125 among controls. I think I did this to make sure we got a good result here. So let's go ahead and do this one. All right, so we got here's our odds. 50 divided by 25 is 2. 100 divided by 125 is 0.8. So again, I set this up so that you can just plug it in and it'll work. So we have the odds ratio is 7. The odds ratio is 2 divided by 0.08. We get 2.5. And again, we go through the same process here of calculating the margin of error. 1 over A plus 1 over B plus 1 over C plus 1 over D. We get the sum. We get the standard error by taking its square root. Get the margin of error by multiplying it by 1.96. We get the natural log of the odds ratio. We add and subtract the margin of error to the natural log of the odds ratio. And then we finally exponentiate. And these are our two values. So what's crucial here is the interpretation. So let's go back to the original question. Using table 3, calculate the odds ratio of exposure given one has disease D. Okay, so we're always doing a comparison, right? That's what the odds ratio is about, making this comparison. So we would say that cases, these are people who have disease D, are 2.5 times more likely to have been exposed to whatever the risk factor is versus controls. So that's our point estimate. And our interval estimate is 1.446, 4.322. So we're 95% certain that the true population odds ratio is somewhere between 1.446 or 4.322. This is our point estimate. This is our actual confidence interval. Okay, so that's what I'm going to do for today. I'm going to go back and take a little walk. I'll tell you, these hills here are they're big. They're seriously big. So a lot of fun walking, visiting Chinatown and all the cool places around here. All right, I'll see you all later. Have a wonderful day.